Okay, we're on. So, first of all, homework 2 is due today. It was straightforward, easy, right? And everybody got, I hope, agreement between theory and simulation. And hope you understand what the difference is, what the point is of the problem. So, we're working on homework 3, and I think I've been going slower than usual, so we're getting kind of jammed up. I've got a few homeworks that I want to still assign. We want to get everything done before the end of the semester. We've got Thanksgiving break coming up. So homework 3 I'd like to make due a week from today. So hope we can finish it today. And it's important. This is probably the hardest single homework. So it's important for you to do it right away and have your questions ready by Tuesday, because that's the only chance you'll have to ask questions. If you wait until Tuesday and haven't started it till then you'll probably be in trouble. So I hope everybody has downloaded homework 3. So before we begin, are there any questions? All right, so in homework 3, what you're asked to do, everything is supposed to come together now, is that we have 4 cases. So we'll call them case 1, 2, 3, and 4. And in case 1, this is the, let's see, we said here that x is a uniform 0, 1. And in case 2, x is exponential with parameter 2. And I spent time last lecture talking about what the exponential means. So we had 2 continuous distributions that have names and have important meanings in terms of physical models. Case number 3 is a simple one where the x is equal to a constant. The way I specified that, as I said, the probability x equals 1/2 is 1. So that constant is 1/2. And case number 4 is just a simple discrete case where the probability that x equals minus 0.2 is 1/2. And the probability that x equals plus 1.2 is 1/2. Okay, so those are the 4 cases, and in each case you're supposed to compute the expected value, the variance, and the probability that x lies in a certain interval. And in our case, the interval was 0.25 and 1.35. And in each case, there are 2 answers. There's theory and simulation. Theory and simulation. Theory and simulation. And then in addition, it asks you to calculate the distribution function, which I'll get to shortly. Now, you already know how to do the theory. I'm going to do most of it, but you should be able to do it now. The simulation is the new part. And so in the simulation, what the simulation does is 2 things. One is the logic tells you, if you didn't already know, exactly what you mean by expected value, variance, and probability. And also, the main thing is that it tells you how to generate random variables with the specific distributions given. So that's the new key concept. So the simulation code you already have. It's in front of you. I discussed this last time. So you're going to put this in a loop, and you're going to generate 10,000 values. And of course, I'm using BASIC because it's an easy pseudocode, but you don't have to use BASIC. Now, in that loop, what you're going to do is you imagine that you have this urn, and the urn has tickets in it. That's the picture I have in my mind. The tickets have numbers on them. The numbers are the realizations of the random variable x. And they're in this urn in the same frequencies that they are in the population. And those frequencies are what's defined by the distribution density function or probability mass function, or name. So what I have to do is I have to reach into this urn and have to pull out a ticket, which is equivalent to, let's say if I were rolling dice, then the values in the urn would be the values of the dice, the probabilities or frequencies with which the numbers values in the urn match the values of the dice would be the probabilities. And so a roll of the dice would be equivalent to pulling out a ticket. So that means I'm going to generate X, and that's the part that I just started last time. That's the key concept. Now, once I've generated the X, what I want to do is I want to calculate the expected value and the variance and this probability. So to calculate the expected value, I have to sum all the values, divide by the number of values. So I'll sum the values, I'll call that sum S1, and then in BASIC I could write S1 is equal to S1 plus X. Everything defaults to 0, so that means that every time I execute this instruction, I'm simply going to accumulate the latest value of X. So when I get all done, after 10,000 times, I've got a sum of 10,000 X's. I'm going to divide that, of course, by 10,000, and that'll give me this simulation value. Then the next statement is 300, and it asks you to calculate S2, which by definition is the sum of the squares of the X's. So every time I get an X, I accumulate its value, I square it and accumulate that value. So at the end, I'm going to get the sum of the squares of the X's, and the reason I want to do that is I want to calculate the variance. And remember, we had a formula that says that the variance is equal to the average of the square minus the square of the average. So the average of the square, well, when I get done, I'll take this S2 and I'll divide by 10,000, and that'll give me the average square, and then I'll subtract from that the square of what I calculated here divided by 10,000, and so that'll give me the variance. Then the next step asks me to calculate the probability the way it was given. It calculates the probability that X is greater than a half. But the problem asks you to calculate the probability that X lies in this region. So that means that what I would do is something like this. I'd say if X is greater than 2.5 and X is less than or equal to 1.35, then C equals C plus 1. So this instruction will simply count how many times X satisfies this requirement. And at the end, when I divide this by 10,000, that'll give me the fraction of values that satisfy that requirement, which then is the model for the probability, or actually probability is the model for that fraction. Okay, statement number 500 says next I. So this just says, okay, do this thing 10,000 times. You could do it 100,000 if you want. It'd take 10 times longer, but this is very fast. You could do it 1,000,000 times. It would still do it in an instant. Then statement number 600, the next statement, asks you to print the values. So I want to print S1 over 10,000. So that's going to give me the average value of X, which is the simulation version of the expected value. Then I'm going to print S2 divided by 10,000, which is the sum of the squares. And then I'm going to average of the squares, and then subtract from that the square of the average, which is S1 divided by 10,000, quantity squared. So that's going to give me the simulation value or version of the variance. And then if I want to calculate the probability of lying between 0.2 and 1.35, I'm going to take C, number of times that occurred, and divide that by 10,000. So that's my code. And I have to add some instructions to calculate the distribution function, which is the second part of the problem, which I'll discuss shortly. So right now, the key is, how do you generate X? So any questions so far? So this is going to be a very powerful technique, because what this does is it allows you, if this works, to have the computer generate values from a population with any random variation, any description at whatever you name, and then you can always use that for answering more complicated questions. So I need some space, so I'm going to erase this, because you have this in front of you, because this is at homework 3. Okay, so now how do you generate x? So you do that using what's called the inverse transform method. Inverse transform method. It's not the only way of doing it, but it's probably the best for our purposes. And what it is for, it's to use the random number generator. So you're assuming that the computer can generate random numbers, has a random number generator. And in fact, we're going to test whether that's true or not. I mean, we know it has it. We're going to test whether or not it works. So we're going to use the random number generator to generate random variable values. In other words, to sample from the urn according to any, so that's the key here, whatever you specify, any specified distribution function. And there's two parts to this. First is the algorithm, that is, this is what you do, and then the second part is the proof that it works. Of course, you don't have to understand the proof to get it to work, but there's really no point to it if you don't, because then I might as well tell you, well, just go to some software that says it generates these variables and use that. And here's the algorithm. The algorithm says this. What I'm going to do is I'm going to illustrate it with a picture. So I have a distribution function, so I have to draw one, so let me make it look like an exponential. So remember, any distribution function has the property that it starts at 0, it ends at 1, and it never oscillates. So suppose that this is a distribution function that I wanted to that describes the tickets in the urn. And I'm going to call this, for the purpose of the proof, U, and I'm going to call this G of U. So this is an arbitrary function that has the properties of a distribution function. It starts at 0, it ends at 1, it doesn't oscillate. Now what I'm going to do is I'm going to pick number R, which is what the random number generator gives me, project over to the curve and down, and call that value X. That's the algorithm. Now, what the theorem says, which I'm going to write down in a moment, and I'll write out this algorithm in a minute, what the theorem says is if the R values, that is, the values that the random number generator gives you, are in fact uniformly distributed between 0 and 1, then the distribution function of X will be whatever G is. Okay, so here is the algorithm, which is, I'm just writing down now what I said. To generate a value X, put random number R on vertical axis, project over to curve G, and down to horizontal axis. All right, so I just stated in words what this picture illustrates. Now, what you have to do in any particular implementation of this is you have to take the formula for G and set, you have to solve backwards. Instead of having r as a function of x, which is the way the graph is drawn, you have to find x as a function of r. That's why it's called the inverse. So whether that's difficult or easy depends on the algebraic formula for t. So sometimes it's easy, sometimes it's hard, but in principle it's always the same thing. As long as there's an inverse, you can solve the equation backwards. This is something, for example, that I learned in, I don't know, maybe it was 9th grade, I think, where you're given y equals f of x, and you have to find the value of x that satisfies the equation. So it's the same thing. Now, the theorem is that if the r is uniform, then x will have its distribution G. So since I'm running out of space, I don't want to erase this. And since the, I guess it's the educational theorists say that we shouldn't have more blackboard space for some reason, let me erase this. So this is about to go. Everybody okay on this? Okay. So nobody said no, so I'll erase it. So you can do anything you want if you ask people to vote for something, and of course nobody votes, so you just state the problem so that you do the opposite. Right? So everybody who abstains, has no opinion, is voting for erasing. Okay, so there's the picture. So now here's the theorem. The theorem says if r is distributed as a uniform variable between 0 and 1, which is what a random number generator is supposed to do. So if that's true, then the distribution function of x evaluated at t is in fact d of t. Okay, so first see what this means, what it says. The algorithm says that what I do is I take my random number, I take my r, I put it on the vertical axis, project over to the curve and down, and that gives me a value of x. Now, r is random. So since r is random, where it projects to is going to be random. So in fact, what this curve does is it takes the original randomness in r and it distorts it into a new kind of randomness. Now, what is the distribution function of the new random variable that I get? That is a distortion, the distorted value of r. The distribution function of x, by definition, that's capital F sub x of t. What is that going to be? The theorem says that if the r happens to be uniform, then the distribution function of x will be exactly whatever that formula is right there. Which means that if I want to generate values for a random variable with any particular distribution function, I just draw the graph of the distribution function, solve it backwards, and that gives me an instruction that gets me x in terms of r. And I'll give examples of that in a minute, but first I want to prove this. So this is kind of a sophisticated theorem, and its proof is so simple that it's one of these things where the hand is quicker than the eye. Okay, so let me write the proof here. So what we want to find is the proof. The proof says that we want to find the distribution function of x. That's the question. If I follow this algorithm, what's the distribution function of x? Now, by definition, that's the same thing as the probability that x is less than or equal to t. So this is definition. That's what distribution function means. But what is that? Well, now we can go from the graph. We're not being mathematically rigorous here, so we allow ourselves to draw pictures. So you can see that, let's draw t. There's t. Now, if x is to be less than or equal to t, that is x lies to the left of t, then if that's t, this value right over here must be g of t, because g is the formula for that curve. So obviously, if x is less than t, then r will be less than g of t. So therefore, the probability that x is less than t is the probability that r is less than or equal to g of t. So this equal sign comes from the picture, or graph, let's say. Okay, now what is that? Well, this is a random variable. That's some number or parameter or something. The probability that the random variable value is less than or equal to that is the distribution function of that random variable, R, evaluated at that, which is g of t. So what's the distribution function of R evaluated at g of t? Well, first of all, we have to write down what the distribution function of R is. So if R is uniform 0, 1, that means that its distribution function is given by this. The distribution function of R evaluated at t is equal to 0 if t is negative, t if t lies between 0 and 1, and 1 if t is greater than 1. Okay, so that is this thing right here. That's the same as that. Now, what this thing says is that if the argument lies between 0 and 1, then the value of the function is equal to its argument. It's a straight line. So therefore, since g of t is this value right here, which necessarily lies between 0 and 1, that means that f sub r of g of t must be g of t. Okay, so this equal sign follows from this right there. Well, case closed. It's done. I proved it. Because the distribution function of x is equal to g. And g is whatever I use to make this mapping. Okay, so this is one of those things where the hand is quicker than the eye. This stuff, of course, is in the book. In advanced books, semi-advanced, in respectable books, like the one we're using, it comes at the end, and actually, for some reason, I'm not sure what it is, it's always looked at as being something that's more sophisticated than necessary. So in our case, this thing is actually proved. This is theorem 11.2, which is on page 476. So it comes at the end of the book. And as I always like to say, it's in disguise. But if you read that, it's at first glance hard to recognize that it's actually the same theorem. On the other hand, if you look at these elementary books, these cookbooks that are written for applications, it's usually not in there. Or they just state the answer and they tell you what to do. They give you the algorithm and they don't tell you why it works. But usually they don't even do that. Usually they just give you special cases. And then you wonder, it looks like some kind of magic formula. Or sometimes they don't even do that. They just say, they just ignore the whole question. Because if you use software, certain software, that is designed for simulation, one of the things that software does is you tell the software the distribution function of the random, or density, or whatever it is, of the random variable that you're trying to simulate, and then it does the work for you. Of course, I never want to fly in an airplane designed by a guy who figured out what the best shape of the wings was using a simulation program that he didn't understand what the random variables were. So far so good. Either I've been lucky or all the people in the planes that I've flown in who designed them actually understood this. Okay, so this is the theorem. What we have to do now is look at some examples and fill in this stuff here. So any questions at this point? All right, so let me, let's see. Okay, let me erase up here. And let's see, I'll leave the picture. So I really don't need this part because this was only used for the proof. Okay, so case number one. Case number one, remember I'm writing instruction number 400 in every case. Or not 400, let's see, maybe it was called 400. What did I call it? Just say generate x, so it's between 100 and 200. So what I'm doing is generate x. Okay, now in case number 1, what I want to do is I want to generate a random variable that's uniformly distributed. So in case number 1, that means that the distribution function that I want looks like this. Because if x is uniform, 0, 1, that means that the graph of its function is simply a straight line. And if this is t, then the formula right here between 0 and 1, which is the important part right there, that simply is g of t or f of t, depending what I'm calling it, equals t. Okay, so instead of a curve like this, in a particular case in which the random variable I want is uniform 0, 1, that means its distribution function looks like that. So if I take a random number and put it on the vertical axis and project over to the curve and down, then what I'm going to get in this case is simply that x equals r, because the function of t equals t. This is just a straight line. So in other words, there is no distortion between that value and that value in the case in which the distribution function that I'm trying to get is the uniform. So in other words, this thing right here corresponds to the distribution function of the random variable that I'm trying to generate. So what does that mean? What this graph says is that x equals r. Am I right? Okay, so therefore, if x equals r, or r equals x, the same thing, that means that my instruction would be x equals r and d. That's my instruction. Okay, why is that? Because the theorem says that if the number that I put on the vertical axis is uniformly distributed, then the x will have the same distribution as whatever the curve is that I'm projecting over to. So if I want to project to if I want to get a uniform distribution, that means that if I apply the inverse transform method, it simply tells me that x and r are the same number. So, in fact, you knew that, because if we start out by assuming that the random number generator gives me values that are uniform between 0 and 1, and I ask you to generate values that are uniform between 0 and 1, then all I would do is take as the value of x whatever the random number generator gives me. The point is here that this is in fact an example of the inverse transform method. Because what the theorem says is that if in fact the random numbers, the numbers that I put on this vertical axis, are uniform, then the projection will be uniform. Okay, so the question is then, are the random numbers, the things that the random number generator gives me directly, are they in fact uniform? Well, that's the responsibility of the person who writes the random number generator. So what he's supposed to do is he's supposed to come up with an algorithm that will produce numbers that, if I took statistics on them, would appear to be uniformly distributed between 0 and 1 and would be independent. Now, they can't be, really, because in fact the way the random number generator works is it generates what are called pseudo-random numbers, which are found by a deterministic algorithm. But they appear to be random, or at least they're supposed to. So we can check to see whether or not this works at least well enough for our purposes. Because what we have to do is look at the theory, then look and see what the simulation, what the theory predicts, what the simulation gives us, and if those things turn out to be close, then what that means is that probably the random number generator is in fact generating uniform variables. So if case number 1 works, then all the other cases should work too. So we're checking in case number 1 to see whether or not in fact the random number generator generates numbers that are uniform between 0 and 1. Okay, so what is the theoretical value here? We have a random variable that's supposed to be uniformly distributed between 0 and 1. What's its expected value? It's 1/2. We've already done that. So that means that when I run the simulation with the instruction x equals r and d, this value should turn out to be very close to 1/2. If it doesn't, then something is wrong. Okay, what about the variance? What's the variance for a uniform random variable, uniform between 0 and 1? We already worked this out as one of the examples. Should be in your notes. It was 1/12. Is that right? Anybody have notes? Anybody taking this course? Okay, so let's say, if my memory is correct, let's say it's 1/12. So what that means is that when you run the simulation and you calculate the part that is variance, the second thing that was printed out, it should be very close to 1/12. If it is, that's consistent with the idea that the random number generator works. Of course, it doesn't prove it does, it's just consistent with it. But if it's not equal to this or close to that, then of course the random number generator is not working. Of course it'll work. I mean, we've done this 1,000 times, and this is a standard random number generator. Which surprisingly, standard random number generators don't always work well enough for real applications, because in real applications you have to generate trillions and trillions of random numbers. But for our purposes, no question, it's going to work. Okay, what about the fraction of x's that lie between 0.25 and 1.35? You already did this. This was one of the parts of homework 0. And we did this also in class as an illustration when we were talking about distribution and density functions. And the answer turned out to be 0.75. So this is what the theory predicts. What will the simulation give us? Well, it's going to give us a number very close to that. Take my word for it. Okay, so let's say you've done this and you got a value, 3 values that agree with those 3 values. So that means that most likely, you're not just lucky or unlucky as the case would be. Most likely, the reason that that works is because the random number generator really does generate numbers that are uniform between 0 and 1. And the theorem says that if the random numbers are uniform between 0 and 1, if that's true, then the distribution function of the values you get from the urn must have whatever distribution function it is that you're using for the projection. And in our case, we're using the numbers directly, which means we're just projecting over the formula, which says f of t equals t. That's that. So it works. So now that we know it works, now we can apply the same thing to these cases. Okay, so any questions about that? Okay, what about the second case? What's the check? What's the expected value of a random variable that's exponentially distributed with a parameter of 2? 1/2. In fact, this is not phony, but this example was constructed so they all 4 random variables have the same expected value. And so this illustrates the fact that knowing only the expected value doesn't really tell you too much, because they're all highly different otherwise. They all have different variances. So this is going to be 1/2. And likewise, this is going to be 1/2 because this is a constant. And you don't have to be Einstein to see that if you have a random variable that half the time takes the value minus 0.2 and half the time takes the value 1.2, that the average is going to be that plus that divided by 2, or 1/2. Because you have to write that out using the formula for expected value, just a sum of 2 terms, but it's also going to be 1/2. Okay, what's the variance going to be? 1/4, because when we discussed the exponential random variable as an example, we said that the variance is equal to 1 over lambda squared, or the mean squared. And since the mean is 1/2, then the variance should be 1/4. What's the probability of lying in that range? I don't remember, but you had to calculate that as part of homework 0. Right? Homework 0, I asked you to calculate an integral, which was, it turns out, the integral of a density function that is a density function of exponential with parameter 2, and the integral limits were 0.25 and 1.35. So you've all done that. Can you tell me what that answer was? Right?
0.539.
What was it?
0.539.
0.539. Okay. 0.539. Okay, how about this one? If the random variable is a constant, which always takes the value 1/2, its expected value is 1/2, what's its variance? 0. That was another one of the examples I did in class. The variance of a constant is 0, obviously, because variance measures how variable a random variable is, and a constant is not variable at all, it's constant. What's the probability that a random variable that always takes the value 1/2 lies between 0.25 and 1.35? 1. Okay, so when you use the inverse transform method, for this case, you should get these values. How about this one? Well, I don't know. This is one I haven't worked out yet. But the variance is obviously, it's a simple formula, so we're going to get some number here, and we're going to get some number here. So I won't work this out, but this is like, except for this, it's the second simplest case, because this is just a discrete random variable that takes two possible values, each with probability 1/2. So whatever it is, I don't know, but you can calculate it. Okay, so we're all done with row number 1. Now we've got to worry about row number 2. So you want to see whether or not the simulation values will give you roughly 1/2, 1/4, and 0.539. Okay, so now I come over here and I implement this theorem. So there's the picture. So here is the graph of the distribution function of the random variable that we're trying to simulate. So the important part, for our purposes, is the part that lies between 0 and 1, because that's where we're going to make our projection. So what's the formula for that curve? Well, if we want the random variable to be exponentially distributed with parameter 2, that means that this part of the graph has formula 1 minus e to the minus 2t. Let's call it lambda for our purposes now. And then later we'll plug in lambda equals 2. So the algorithm says set this equal to that. So in other words, if I plug x into this formula, I would find that r is equal to 1 minus e to the minus lambda x. Right? So this is t. I replace the value of t by x, plug into the formula. That gives me the relationship between r and x. But I want to get x as a function of r. So I have to solve this backwards. So I'll rewrite this as e to the minus lambda x is equal to 1 minus r. Let's erase some stuff here. I'll take logarithms of both sides, which means that minus lambda x is equal to the log of 1 minus r. Which means that x is equal to minus 1 over lambda natural log 1 minus r. So that's the mathematical formula. So I have to write, in my code, I have to write something that says, take the random number generator value, plug into this formula, and call that value x. And if I do that, then if r's are uniform, in other words, if the random number generator works, and we've indicated, I hope, that it does work because we see agreement for case number 1. So if the random number generator works, then the x values will be exponentially distributed with an average of 1/2, which means that when I run the simulation, the values I get for here, here, and here should be close to 1/2, 1/4, and 0.539. So in BASIC, how would I write this instruction? X equals minus, let's see, we've got 1 over lambda. In our case, lambda is 2. So I would write it as minus 1 over 2 times logarithm. In BASIC, the natural log is log. I don't know why, because you'd think it would be ln, because log usually means base 10, but that's the way at least my BASIC works. But whatever it is, whatever language you're using, you have to know how to calculate a logarithm. Okay, so this is a natural log log, and then inside I have 1 minus r. But R is now what the random number generator gives me. So this is my instruction. So every time this instruction is executed, the random number generator is called. It gives me a number between 0 and 1. It calculates the logarithm. Now, since the random number is always between 0 and 1, 1 minus that will always be between 0 and 1, which means that the logarithm of it will be negative, and that will cancel that negative sign. And the 1/2 is just a scale factor. Because in general, what this tells me is that the inverse transform method here gives me, with a logarithm, it gives me an exponential random variable whose average is 1. And then by multiplying by 1 over lambda, I change the scale so I make the average fit with whatever the lambda happens to be. So in our case, lambda is 2, which means the average is 1/2. So that's the instruction.
I have a question.
Yeah.
Why is that 1 minus e to the lambda t and not 1 minus lambda times e to the minus t?
Distribution function for an exponential. Okay, if x is exponential with parameter lambda, what that means is the distribution function is equal to 0 if t is negative and 1 minus e to the minus lambda t if t is not negative. Now remember, that's how we derive this. Except that we derive greater than and then subtract it from 1 to get less than or equal to. Then to get the density function, you differentiate that.
Right, that's where the lambda comes in.
Right, that's where the lambda comes in. The density function for that guy right there, which is the derivative of this, is 0, obviously there. Differentiate that, I get lambda e to the minus lambda 2. In homework 0, I gave you this and asked you to integrate it, and you got that. Go back and forth. So if I want to calculate, for example, the expected value of a random variable, at least the way we did it in class, I need the density function. But if I want to generate random variable values in a simulation, I need the distribution function. So they're equivalent, but you have to be able to go from one to the other. So typically what's going to happen on a final exam is I'm going to have a question that will say something like, suppose that in homework 3, remember it'll be open books, you'll have the homeworks right in front of you, if you did them. So if you didn't, you suffer twice because you don't get the points for the homework and you can't do the exam. So it'll say something like, in homework 3, suppose that x is described by, and then I'll give you some density or distribution function or probability mass function. Of course, it won't be one of these. It'll be something different, but it'll be the same idea. And then one question would be something like, find the probability that. So that means that you would have to integrate it or add if it's discrete. Find the expected value. That means that if I gave you the distribution function, you'd have to differentiate to get the density function and perform that integration. Of course, on the exam, it'll always be something that's really simple as long as you know what to do, but the actual differentiation or integration will always be easy. Then the question will say, if you were simulating this, write an instruction that would generate values of this random variable. And then that means you have to use the distribution function and write this equation like this, and then solve it backwards. Of course, it wouldn't be the exponential because you already know that one. It would just be something else. Now, what the problem people have is that a lot of people can't seem to learn the difference between distribution function and density function. So whichever one I state, that's the one they use. So that means they get half of it right. Because if the question requires you to use distribution function and density function, and you use the density function for both parts, then one part's going to be right and one's going to be wrong. And the other thing is that you have to understand this. You don't have to understand it to do this one because I'm already doing it for you. But you have to ask yourself as you go along, suppose that this formula right over here were different. Then how would I do it? Of course, here I'm going to give you 4 examples, but of course the one that's going to be on the final exam is not going to be one of the examples you've already seen. It's just going to be similar. So you have to be able to recognize, you have to be able to understand how you have an equation which represents the dependent variable in terms of the independent variable and solves it backwards, finds the inverse, which, as I say, is algebra at the 9th grade level, at least when I took algebra. Is there a question back there? I thought I saw a hand. No? Okay. Okay, how about the next one? Okay, how am I going to do that? Well, first of all, we already know what the answer's got to be, because if I have an urn in which every value is the same value, namely 1/2, then obviously the instruction is going to be x equals 1/2. 0.5, however you want to write it. But how do I get that out of the inverse transform method? Well, what I don't have to do is I have to draw the distribution function of x. So what you're given is the probability that x equals 1/2 is equal to 1. That's a probability mass function. How do you get the distribution function from a discrete random variable? Well, here is the distribution function, which is the probability that x is less than or equal to t. There's t. This is a random variable. It takes one value. The value is 1/2. And so the way in which you go from the probability mass function to the probability distribution function is you have a step function in which the steps occur at the values the random variable takes. In this case, there's only one value. And the height of the steps are the probabilities. So in this case, the function steps from 0 to 1, like this. So this is the graph. Of course, this is discontinuity there, so technically the value of the function at 1/2 is right there. Okay, so this is the distribution function that we already saw for this. This was one of the examples I worked out earlier. So to be technical about it, it's 0 if t is negative, and it's 1 if t is greater than or equal to 1/2. That's the formula for that picture. Now, the inverse transform method says take your value of your random variable, your r, your random number, put it on the vertical axis, project over to the curve and down. Well, mathematically, it gets messy because you're talking about projecting over to a value where there's a discontinuity. But as soon as you draw the picture, you can see exactly what's going on. You're going to project right over the step and down. And since r lies between 0 and 1, no matter what value of r you get between 0 and 1, it's always going to project over to the same place and down to the same place. So the inverse of this picture is that r equals 1/2, or in other words, the value of x is 1/2, because x is the value that you project to. So x equals 1/2. So this is common sense, but it falls right out of the inverse transform method.
Wouldn't it be
Yeah.
0 when t is less than 1/2?
What was that?
Wouldn't it be 0 when t is less than 1/2?
Yes, that's a mistake here. Thank you. Less than 1/2. That's what's called a thinko. Mental typo. Okay, this case is the same one. I don't want to do it for you, but it's the same idea. The distribution function is going to be a step function, but now it's going to have two steps, one at minus 0.2 and one at plus 1.2. And in this case, one of them is negative, so that means that your graph is going to look something like this. Very quickly, it'll look something like that. So you may have to project over to the negative side or to the positive side. You should be able to figure that out. But the theory is simple. So again, the theory and the simulation should agree or be very close. And if they don't, then you know that something's wrong. So everything is done except this one, which is trivial. Okay? So now you have the power to write a simulation that as long as someone tells you what the description of the random variable is, either its density function distribution function, its probability mass function, or if it's a common one, its name, that you could then use a computer to generate values which are samples from the population, infinite population in principle, that formula, either distribution function, density function, or probability mass function, describes. So any probability problem now can be handled experimentally by simulation. In reality, if you're actually using this stuff in engineering, you have to be able to understand both the theory part and the simulation part. If you don't want to rely solely, especially in a complicated problem, on simulation values, because they're only sample values. You really don't know what you're doing, you just get numbers. So the theory guides you, it tells you what's going on, and you always want to solve a problem theoretically if possible. But real problems are usually too difficult to solve theoretically. And I'm going to give you an example at the end when we talk about the queuing problem, in which there's sort of a boundary. Some of it can be done by theory, some of it can't be, and this is typical for real-life applications of probability in engineering. So now all I got to do is talk about the second part of the problem, which is the distribution function. So any questions? So once you see this, once you do this, even though it may be a little bit time-consuming at first, if you actually do it, you can't possibly not understand what I'm talking about now. So probability should make sense because you can see from the simulation code exactly what it is you're measuring. And the theory should make sense because you can see the agreement between the theory and the simulation. And the inverse transform should make sense because it'll show you that you can generate random variable values with any distribution, whatever you specify. And this also illustrates the fact that I'm going to have 4 different cases, all with the same average value. But I'm going to have different values for the variance and for the probabilities. Okay, now I'd like to make a little bit more careful comparison. So now I'm going to compare the whole distribution function as follows. So now I want to draw some graphs, or you're going to draw some graphs. And yeah, so let me write down first. You're going to have to draw some graphs, except for the case of the exponential. They can all be done with just a ruler. The exponential case you've already done for homework 0, but now you have to do it accurately because you're going to compare theory and simulation. And so one thing you could do, I'll write this down, there's a website where you can download graph paper. www.mathematics, mathematics, mathematics help, HELP, central, CENTRAL, dot com/graph, GRAPH, whatever you call that thing. What do you call it? Underscore, okay. Underscore. Paper.htm. So if you go to that website, you can, I think, download various kinds of graph paper, so whatever scale you want. That's if you're going to do it by hand. It's better to do it by using software that will draw the theoretical curve for you and then put the points on the curve. So if you know how to do that, do it using something like Maple. But if you don't know how to do it, don't worry about it because that's not part of this course, although it's a good thing to know. Okay, so now what does it ask you to do? For each case, and there are 4 cases, it says you want to look at the distribution function. So this is big F. And there are going to be 4 cases. So here's case 1, 2, 3, 4. And for each of those cases, there's going to be theory and simulation. Theory, simulation. Theory, simulation. Theory, simulation. And what you want to do is you want to compare the theoretical distribution function values with the simulation distribution function values. So to do that in this tabular form, we'll just look at it for specific values of t. So here are the values of t, and they are minus 0.25, 0, plus 0.25, 0.50, 0.75, 1.0, 1.25, 1.50. So in a simulation, for each case, you want to calculate capital F evaluated at this value, and capital F evaluated at this value, and capital F evaluated at this value. So that means you have to add some instructions to the simulation. Okay, so let me write down what you would add. Okay, what is capital F evaluated at t? It's the probability that x is less than or equal to t, or in other words, it's the fraction of x is less than or equal to t. So I would say for this one, this is very inelegant. You might be able to do better, but let's get the point across. I'd say something like this. If the value of x that I just computed is less than or equal to minus 0.25, then let's say C1 is equal to C1 plus 1. And then a statement, if x is less than or equal to 0, then C2 is equal to C2 plus 1. If x is less than or equal to 0.25, then C3 is equal to C3 plus 1. So if you're a straightforward, boring programmer, you could just write this instruction 1, 2, 3, 4, 5, 6, 7, 8 times. Now, at the end, when you run it, you will then have counted how many times this event occurred, how many times this event occurred, and so forth. And then to calculate the probabilities, the simulation values, what you do is you divide C1. All right, so you would divide C1 by 10,000, and that would give you the fraction of values that are less than or equal to this value. So you would write that there. And then it would be C2 divided by 10,000 and so forth. So you print each of those values, and then you write those values here. The first one, the second one, the third one, and so forth. And this is all done in one run. That is, there's one run, and in that one run, you're calculating the fraction of values less than or equal to that, fraction of values less than or equal to that, fraction of values less than or equal to that, and so on. And then you make this run 4 times. Actually, you need to do, one way to do it is do 4 runs. The first run, you do the upper half, and you do these instructions as well. So the first run gives you the answers to row 1 in your graph, and then column 1. And then the second run does row 2 and column 2, and so on. So you run the program 4 times, one for each of the different random variables, and you put the answers in here. Then you compare that with theory. Okay, so let's look at this case right here. Let's look at the uniform. In theory, what is capital F evaluated at minus 0.25? 0. What's capital F evaluated at 0? What's capital F evaluated at 0.25? Right. In fact, remember that in case number 1, the graph looks like this. It's just a straight line. Let's see. There's 0, there's 1, there's 1. The graph looks like this. So the function is 0 here, it's 1 here, and it's exactly equal to the value of the argument between 0 and 1. So this would be 0.25, 0.50, 0.75, 1.0, 1.0, 1.0. Those are the theory values. Of course, you're supposed to write all this out, and I just copy down what I'm writing on the board. But all I'm doing is plugging into the formula for the distribution function for the uniform. Okay, now what does the simulation give me? Well, it's going to give me values here, which better be very close to the values theory predicts. If it does, that means that the random number generator works. And if it doesn't, that means the random number generator does not work. Okay, so then it says, plot this on a graph. So now we have these values here. And let me see, I won't write them down yet. Of course, there's simulation output, but you could predict what they're going to be. For example, let's go back to the prediction. What's this value going to be? The simulation is going to give me 0 because it's never going to see a value less than or equal to 0.25. So it's going to give me a value 0 here. It's going to give me a value 0 here. It doesn't give me exactly 0, then you must have made a mistake. But here, I don't know, because in theory it's supposed to be less than or equal to 0.25 a quarter of the time. But it might turn out to be actually, in practice, when you run the simulation, it might be 0.26 or 0.24, who knows. So it's going to be roughly that. This will be roughly 1/2. This will be roughly 3/4. But this will be exactly 1, because it'll always be less than or equal to 1. So that'll be 1, that'll be 1, that'll be 1. So these numbers better be exact, but these numbers will vary. So let's say now it asks you to draw the graph. Okay, so here's case number 1. So here is the distribution function of x evaluated at t, and its formula is 0 if t is negative, t if t lies between 0 and 1, and 1 if t is greater than 1. If you draw the graph, it looks like this, because you already did this in homework 0. 0, 1, t. Make sure you label everything. Students have a tendency to draw graphs and they don't label what the scale is. That's really not worth a lot. Then you draw the graph. Okay, so you have a ruler, you draw a straight line. That's what the theoretical graph looks like. Now, it asks you to put on the theoretical graph the simulation values. In other words, the values I'm going to get from this column. Okay, so what are they? Well, first of all, I have to indicate on the graph the point where that's going to happen. So there's minus 0.25. Here is plus 0.25. Here's plus 0.50. Plus 0.75, 1, 1.25, 1.50. Now, when you run the simulation, this value will be exactly 0. So you indicate that by writing a point on the graph. Remember that the theoretical graph is for every t, but the simulation tests only the particular ones that you have the patience to put in the program. This is going to be exactly 0. This one, now, at 0.25, maybe it'll be a little bit less, like that. And at 0.5, maybe it'll be a little bit less. And at 0.75, maybe it'll be a little bit more. And at 1, it should be exactly on 1.25, 1.50. So that's what your graph should look like. Now, when you do it, if these points don't lie exactly on the theoretical curve, I know you made a mistake. If these points do lie exactly on the theoretical curve, I know you didn't actually do it. Right? I mean, if you see 100% agreement, then it's suspicious. On the other hand, if these points don't lie close to the curve, then that means that you also made a mistake or the random number generator doesn't work. But suppose you ran it and the points came out looking like this. Well, obviously that's wrong. So what this picture shows you is that you see that the simulation points are going to lie very close to what theory predicts, and that's the whole point of the problem, to show you what the relationship between the two is. Now, in case number 1, 3, and 4, the graphs are all just step functions or straight lines. So you don't need any fancy graph paper or any fancy software. But for case number 2, then you actually have to draw the graph correctly. So here's case number 2. Now, the distribution function of x evaluated at t is equal to 0 if t is negative. That's it right there. And it's equal to 1 minus e to the minus 2t, lambda is 2 in our case, if t is not negative. And you've already drawn the graph of this, because you did this in homework 0, but people did it with various degrees of accuracy. Most people didn't actually plot the graph, they just drew a curve. If I spotted that, I took points off for it. But you should have a smooth curve, and this curve should be as exact as possible. And of course, the way to do this, one way to do it, is, if you're doing it by hand, is you simply write a little program. You already have a program, so you can include this, in which you put the values of t, and then you ask the program as a calculator to calculate 1 minus e to the minus 2t. So for the values of t, those are the values that go along the horizontal axis. These are the values along the vertical axis. You connect the points, but you shouldn't really see the points, because remember, you're supposed to be doing it in theory for every point. The particular values of t that are indicated here are the ones that are going to be in this table. So this value, of course, is going to be 0. This value is going to be 0. This value is going to be 1 minus e to the minus 0.25 times 2. Right? This value right there. 1 minus e to the minus lambda, which is 2, times 0.25. That's the value of t. So whatever that number is, that's what sits in there. There's always someone who writes down the formula, not the number. Okay. What they're trying to indicate is that they're too lazy, or they don't have their calculator with them, or something like that. What it really means is they don't know how to calculate it. Okay, so that's supposed to be a number, but it's calculated from this formula. And now, you take the simulation values, okay, whatever you got when you ran the simulation, and you do the same thing you did here. So here is minus 0.25, here is 0, here is plus 0.25, here is 50, 75, 1.0, 1.25, 1.50. And now, whatever the simulation value gave you, so what should happen is the values you get should lie very close to the curve, because it has to. I mean, this is a tautology. That's why I call it a dumb exercise. It has to work. The only reason it wouldn't work is if the random number generator doesn't work, which we know for our purposes it does. It's accurate enough. And otherwise, it has to work, because everything is internally consistent. If it didn't work, that means that logic doesn't work, and atoms would fly apart, and the whole universe would go to hell. Couldn't possibly be. If it turns out that pi, for example, is 3.14, and that's the end of it, there is no world, and everything has to be logically consistent. So what should happen is you should get points that are very close to the curve, but not exactly, ordinarily, on the curve, because there's error in the random number generator. There's two kinds of error. One is, well, you've only generated 10,000 values, not an infinite number of values. And the second error is that the random number generator doesn't generate random numbers anyhow. It's only an approximation. But once you do it, you should be convinced beyond the shadow of a doubt that everything works. Everything is internally consistent, and there's no doubt that in an exponential case, you get a picture that looks like that. In the uniform case, you get a picture that looks like that. In the other two cases, again, you'll get similar agreement. The other two cases, remember, the graph is just a step function. So that's it. So this could take a while to do. That's why I urge you to get started quickly, because you'll probably have some questions. But once you see what's going on, it's straightforward. The trick is to understand it, because, as I say, this is the key to everything. and this stuff will be on the final, only the names will be changed to protect the innocent. Okay, any questions? I hope everybody's in agreement that this shows how everything fits together. It all works. All right, let me just say something about the random number generator. So this is going to be due Thursday, so you should do it over the weekend and have your questions ready on Tuesday. And then homework 4 is an extension or continuation of this. But homework 4 is actually easier, but you can't do it at all until you've done homework 3. Okay, how does a random number generator work? It works, it's a pseudo-random number generator. Pseudo, P-S-E-U-D-O, that means fake or false. So it's a pseudo-random number generator. So it generates fake random numbers. So let me give you an example. It does it by a deterministic algorithm. So here's a possible way I could do it. Not the way it's done, but I could do it. I could take the value pi, 3.14159, so on. I don't remember what these things are. So I get all these integers. And then I could say, okay, now the way I'm going to do it is I'm going to pick some starting point, maybe at random or just pick one. And then I'm going to call my first random number point that. And then my second random number will be point those two. And the third one will be those two, and so forth. Now, pi is a transcendental number. So essentially what that means is that it never repeats itself, and roughly you could say each integer is going to occur, sort of, you would think, independently of each other integer 1/10 of the time. So if you look at these random numbers, they would probably look like they're uniformly distributed. So this is a deterministic algorithm. And you could write a program that computes these. You would always get exactly the same random number stream. The random numbers would be computed by a deterministic algorithm, but they would look random. But now, let's suppose you're looking at these numbers and you said, wait a minute, this is the 65th and 66th digit in the expansion of pi, and this is the 67th and 68th, and as soon as you realize that, the numbers are no longer random because you could predict every one of them with absolute accuracy. So what a random number generator does is it has a deterministic algorithm that generates numbers such that if you knew the algorithm, you could predict exactly what they are. They're deterministic algorithm. But they give the appearance of being random. The trick for the person who writes the random number generator is to write something in which the calculation is made very quickly, because you've got to be able to do billions or trillions of these things. And so it has to be cheap, but at the same time, they have to pass tests for statistical independence. They have to look like they're independent, and they have to look like they're uniformly distributed. So that's the trick, and that's a whole, you could spend your life on that question itself. But for our purposes, it's done. We use the random number generator, whatever it is that's in the operating system. Okay, any questions? All right, so work on this, have your questions ready by Tuesday, and then we'll start looking at homework 4. All right, thank you. Let's write something down.